Hi everyone! This video will open you a completely new horizon. It will connect two big worlds that you know very well, most likely, but you might not know how closely related they are. Let's not be so mysterious and let's reveal our hand. The first big world is, clearly, the maximum likelihood method that we explained in the previous videos. The second one is the least squares method. The latter has been an extremely successful tool for more than 200 years. It was developed by giants of mathematics, Legendre, and yes, the foremost of mathematicians, Gauss. However, let's say it openly, the least squares method can be derived just as a special case of the maximum likelihood method, and we will be done with it very fast. Let's define our playground now. Assume you've bought a dosimeter and you are measuring the dose from a nuclear reactor that you've built in your living room. You want to measure the dose as a function of the distance from the living room. You have an idea how the functional dependence of the dose on the distance could look like, and you want to determine the function parameters. The manufacturer calibrated the dosimeter, and the device provides an uncertainty corresponding to each measurement. The uncertainty is perfectly Gaussian. Let's list the assumptions in a mathematical language now. The least squares method assumes that we are drawing events from Gaussian PDFs. Each event can be drawn from a different PDF, but all PDFs must be Gaussian. Moreover, we have to know the parameter sigma of each Gaussian distribution. So, the only unknowns are the mean values of the Gaussian PDFs. The means follow some functional prescription that contains unknown parameters. The function doesn't need to be a PDF. The goal of the least squares method is to estimate its unknown parameters. After all the videos on the maximum likelihood method, it is super easy for you to build the likelihood function for this situation. Here we go! L as a function of theta vector is equal to the product of I equal to 1 to n of normal distributions n of the variable xi ops given parameters xi as a function of Ri and parameters theta vector and sigma I. As usual, the measured or observed data are denoted as xi ops. Xi is the function describing the relation between means of the different Gaussian PDFs. The function depends on a variable r that is assumed not to be random. In the present example, Ri stands for a distance from the living room, and it is assumed to be determined very precisely. Least squares estimators of the parameters theta vector are values for which a function called chi-square has its minimum. Oh yes, the function is called chi-square in order to maximize confusion. Let me stress that this chi-square is a different function than the chi-square distribution. However, as you will see later, there is a relation between this chi-square function and the chi-square distribution. The present chi-square function looks like this. Chi-square as a function of theta vector is equal to the sum of I equal to 1 to n xi ops minus xi, function of Ri given theta vector, all this squared over sigma I squared. The estimators of the parameter theta vector are the same as the maximum likelihood estimators. This can be seen very easily if you calculate the negative logarithm of the likelihood function we have just written down. You will get exactly the same expression. Everything we said until now can be generalized to a situation when the individual measurements aren't independent, but the joint PDF for the set of all measurements is an n-dimensional Gaussian with a covariance matrix V. Then the function chi-square, to be minimized, looks like this. Chi-square, the function of theta vector, is equal to the sum from ij equal to 1 to n xi ops minus xi, function of ri, given theta vector, all this times inverse of v, element ij, all this times xj ops minus xi of rj given theta vector. Again, we can see that the function minimum is at the same point as the maximum of the likelihood. All this was meant to say that under the special circumstances we've just described, the maximum likelihood method yields the least squares method. On the other hand, we should emphasize that the least squares method lives its own life, and people use it even in situations when it doesn't coincide with the maximum likelihood method. These are situations when the PDFs aren't perfectly Gaussian and or when the sigma parameters aren't really known, but they are estimated. Let's study the least squares method a bit. Let's keep all the previous assumptions, and on top of them, let's assume that the functional relation between the Gaussian mean values is linear in the parameters theta vector. For example, a polynomial function sum over n theta n r to the power of n is linear in the parameters theta n. In general, we can write our assumption as xi of r given theta vector is equal to the sum j equal to 1 to m ij of r theta j. Then, if this is the correct functional dependence of the Gaussian mean values on R, we are getting a wonderful property. The value of the chi-square function at its minimum is distributed according to the chi-square distribution. The number of degrees of freedom of the chi-square distribution is n minus m, the number of measurements we did minus the number of parameters we estimated with the least squares method. People use this amazing fact to test whether the function xi describes the data well or not. This test is extremely simple, but really powerful if all the assumptions hold. It's enough to note that an unsuitable function xi would result in a high value of the chi-square function at its minimum. As a figure of merit, people take the integral over the chi-square distribution from the observed minimal value of the chi-square function to infinity. This integral is called p-value, and it is going to play a key role in the next big chapter on hypothesis testing. A low p-value means that it is very unlikely to observe a minimum chi-square function value as high as we observed or higher if the function xi describes reality. Oof, that's complicated. You wouldn't say it like this to a journalist. Incorrectly, but comprehensibly, you would say that it is unlikely that your function xi is correct. Moreover, if you were a politician, you would stop calling the function yours. Another topic that's worth spending a couple of minutes on is the combination of measurements with the least squares method. The setup is the following. We have a certain number of measurements xi of the same parameter. Let's call the parameter xi. The model for each measurement is a Gaussian distribution. All the distributions have the same mean equal to the parameter xi, but their standard deviations are different. The overall PDF is a product of the Gaussians, and the maximum likelihood estimator is found by maximizing the chi-square function given by the following prescription. Chi-square of xi is equal to the sum over I equal to 1 to n, xi minus xi, all this squared, over sigma I squared. Apparently, the combination of measurements of the same quantity is just a special case of the least squares method itself. Recall that the prescription of the chi-square function defines the method and that people use it even in situations that somewhat deviate from the original assumptions of Gaussianity of the underlying PDFs. Let's write down the very well-known formula for the combination results. The parameter estimator after the combination is xi hat is equal to sum over I equal to 1 to n xi over sigma I squared, all this over a sum I equal to 1 to n 1 over sigma I squared. The variance of this estimator is V of xi hat is equal to 1 over a sum over I equal to 1 to n 1 over sigma I squared. This is also an extremely known formula. Let's move to the last topic of this video now. Recall that the histogram is in fact a simultaneous observation of n numbers and I. The numbers are typically called bin contents. The most common assumption in particle physics is that the bin contents are independent random variables distributed according to the Poisson PDF. Let's focus on this situation now. In general, a Poisson PDF is different from the Gaussian distribution, and therefore we cannot expect the least squares estimators to be the same as the maximum likelihood ones. Another particularity of the histogram fitting is that variances of the bin contents are unknown. The most straightforward way how to handle the unknown variances is just to estimate them and insert to the chi-square function. The variance of a Poisson distributed random variable is equal to the mean value. If we are fitting a PDF f of theta vector, then the mean value and variance of a bin content are given by an integral over the bin range. We can write it down. Nu I of theta vector over nu of theta vector is equal to the integral going from xi min to xi max f of x given theta vector dx. Clearly, nu stands for the expected total number of events in the histogram. Then the chi-square function looks like this. Chi-square of theta vector is equal to the sum over I equal to 1 to n, ni minus nu I of theta vector, all this squared, over nu I of theta vector. A less accurate but more common way is to estimate the variances with the observed numbers of events. In this case, we just replace nu I with ni in the denominator. What concerns properties of estimators obtained with this method, they approach the maximum likelihood estimators if the expected bin contents are sufficiently high. If they are high, then the Poisson PDFs converge to the Gaussian ones. The word high is obviously not defined quantitatively, but it should definitely be at least 5 or 6 events per bin.